Okay, good morning, everyone. So I work mainly in autonomous vehicle, and the focus of my talk will be how we can integrate autonomous vehicle in crowds or crowded environment. Okay. Yeah. Okay, so you have heard about autonomous cars, like the Tesla, that start to work in urban environment. But the problem remains when the autonomous vehicle navigate shared space, where they have to share the space with pedestrians, bicycles, other vehicles, and many kind of road users. You have environments that are not very well structured. You have roads or streets that are crowded, like in Rome, in the center of the image. You have to deal with flow of people that you have to cross. There is no navigable space, so that you cannot plan in a free space, so you have to go through this crowd. You have to change lane, even if there is no space to change lane. And that's a big problem in autonomous car. So the aim of my work is to try to develop navigation systems that are suitable for shared space with road users. So to succeed, we need to tackle many scientific problems. Some problems with perception, and scene understanding. So we have to detect people, track them, predict their trajectory or behaviors. And even if they are numerous, and even if we don't know the environment, we have to understand the pedestrian's intention and willingness to cooperate. Have they seen the car? Will the pedestrian cross in front of the car? Will it stop to let the car pass, etc.? We have to plan trajectory in dynamic environments where the environment is not predictable, not easily predictable, and heavily populated. So there is little free space to plan the trajectory, and as it's very dynamic and not always predictable, we have to replan constantly. If we don't know, but we would like not to replan constantly, but usually we do. And we have to take care about safety of people and for the car also. And we have to deal with acceptance for people around the car and people in the car. And we need to obtain socially acceptable behaviors. So for the passenger in the car, so they feel safe, for people around, and we need to have readable, legible behaviors. So we need to work on all these domains. I will not present work on all these domains. I will focus on 3 problems. How can we predict crowds and pedestrian behaviors around a car? How we can navigate crowds? And how can we test our algorithm with cars? So the first work I will present is a work that we did with Manon Prédumeau, PhD, which is how to simulate crowds around vehicles. So we can observe that pedestrians have a limited perception of their environment and a limited attention in this perception space. They also have a personal space whose shapes depends on the situation, and they want this personal space to be respected. And they have a behavior in terms of trajectories that depends on the crowd density. So we started to model these crowds using, as far as we can, realistic behaviors of pedestrians. We try to validate these behaviors with real data. And the main objective is that we want to predict the trajectory of pedestrians around vehicles, taking into account the limited perception and attention, the personal space, the density of the crowd, the fact that people are in groups, that there are children, they are in hurry, etc. And we started from the model of a social force model. So just to remind you, because it's quite well known, but social force model the behavior of people with force. You have attractive forces that the pedestrian can be attracted toward its goal, and you have repulsive forces because of pedestrian around the pedestrian studied, and repulsive force with walls, for example. It doesn't take into account the limited perception, groups, personal spaces, etc. So we added some information in this model. We added the perception and attention model. We added an adaptive personal space, and we model also groups that maybe they don't want to split if they have to avoid a vehicle or other people. It was not enough to deal with conflict with AVs, so we added a decision model. So when a pedestrian is in conflict with a car, then he can decide if it has to run, stop, step back, turn sharply, or follow a group decision. So we have a kind of personal space or dangerous space of the car. We have the information, we have to study the trajectory of the car and the pedestrians to see the configuration when the pedestrian and the car will be in conflict. We have a decision model to manage all these constraints. What we did, so maybe I can... So we have simulated crowds using this model, and we have validated the simulation using real data. So we took from the state-of-the-art real data, when on the left you see people interacting with a car, and you have various behaviors, people that are running or stepping back, etc. And we tried to compare, we compared with what we simulated. Obviously, the trajectory are not exactly the same, but the behavior are quite the same. So you see people stopping to let the car pass, etc. Okay. We build a simulator that is available on GitHub, and that can be merged with a navigation system with, thanks to ROS. And so then we can put some model of behavior for the car and have crowds that adapt to the behavior of the car. Here the car is remotely controlled with a joystick, but we will see then what we have done with this simulator. So we have this simulator that can be useful for testing navigation strategies, and so I will show you what we have done in the navigation part. So this is the work of the PhD of Maria Kaptul on proactive, cooperative, and social navigation. So in this work, we focused on the problem of the interaction between pedestrian and vehicles, and how the car should behave when it is in interaction with a pedestrian. So we start from the fact that we have a cooperative pedestrians and non-cooperative pedestrians. So we decided to try to find a model that recognizes if a pedestrian will be cooperative or not. And then when we know that, when we estimate the cooperation factor of this pedestrian, we can adapt the strategy of the vehicle. If the vehicle is not if the pedestrian is not cooperative, then the car will stop to let the pedestrian pass. But if we estimate that the pedestrian can be cooperative, then we can influence its trajectory moving proactively. So that's the main idea of the system. So we have a global path for the car, and we will adapt the local path with regard to the pedestrian behavior estimation. So how we can estimate the cooperation factor of pedestrian and deduce the trajectory that they will follow. So we started from the fact that we have pedestrian pose velocity and goal, we have vehicle pose velocity and goal, and we can build a kind of personal space or interaction space around the person and estimate if the car will enter in this space. So we call that the personal zone deformation. And we have also probability of collision, and we build a cooperation model that gives a cooperation factor. So a pedestrian will be cooperative if it avoids largely the trajectory of the car, and uncooperative if it doesn't move from its own trajectory. This cooperation factor is function of personal parameters, so the mean longitudinal velocity of the agent's goal, the density of the space surrounding the agent, the deformation of the personal zone, and the probability of collision between the pedestrian and the vehicle. When we have this cooperation factor, then we can estimate the future trajectory of the pedestrian. Well, we need it to predict what will be the environment in the near future. So this trajectory prediction model is based on the influence that pedestrians have together, the influence the vehicle has on the pedestrians, and the destination influence of people and cars. We tune our model using two data sets. One taken in Nantes with their own car and people, researchers around, and the data set I showed you for the validation of the simulator. We had the manual annotation of the agent's cooperation. We try to minimize the error in the mean value of the cooperation factor and maximize the cross-correlation between similarly annotated agents in one simulation. So I will show you what we obtain. So you will see the behavior of two persons. One is cooperative, the other one is not cooperative. So one will run in front of the car, the one will stop. And you see the evolution of our cooperation factor on the left. So you have the two persons. You have one is not cooperative. You have his cooperation factor that is going down. And the ones that stop to let the car pass that have a cooperation factor that increases. So now, as we have this model of cooperation, we can adapt the trajectory, the local trajectory of the vehicle with regard to the global path and the behavior estimated for each pedestrian. So the idea was to find the longitudinal control that maximizes the pedestrians' cooperation while ensuring the safety constraint. So it's a function that depends on the number of pedestrians in the influence zone, the cooperation factor, and the safety index that we estimated. We tested our algorithm using this model. We call that the proactive model, and we compare it to a reactive model that stops when there is a risk. And if you look, so you have a flow of pedestrians, 66 pedestrians that have various cooperation factors. And you have in the top the behavior of the car that go through the crowd. And you have the reactive one below that doesn't go through because it reacts to the fact that there is somebody in front and that it cannot go ahead. We compared also the travel time. So we compare a scenario where you have a car that reaches a goal without pedestrians. And we computed the travel time, the mean of the travel time. And we had scenarios where you have the car that has to go to the goal, but there are many pedestrians around. And we observe that with the proactive mode, we lose much less time to reach the goal than if you have a reactive mode. The benefit of this proactivity is that even with 1 degree of proactive control, we improve the navigation performances. And we avoid the freezing robot problem in dense scenarios. We have a gain in terms of travel time, and we estimate that this navigation is more socially compliant. We added a lateral control, so if we need to avoid a flow of person, maybe we can change the trajectory. And so to do that, we divide the space around the vehicle into channels, and we compute a cost for each channel. So this cost is depends on the cost of disturbing the pedestrian in the selected zone, the cost of going from the current location to the goal channel, and the cost of going back to the global path from the selected channel. So we have cost for each channel, and we estimate which channel is the best and plan the local trajectory to switch from one channel to another. We combine this model with our simulator, crowd simulator. And we tested on many scenarios with very dense crowds. So you see the channels around the vehicle that are evaluated, and you see the cars that try to move. Sometimes it cannot move, but when it finds a way to move, it goes through the crowd. And for people that are doing planning, I think they can imagine that usually the robots cannot move in this kind of scenario. So welcome, Maria, which did this work for your PhD. Just in case you want some more details. So we have a crowd simulator. We have a navigation framework, proactive navigation framework. But all this is in simulation. And one big problem we have with cars is that we cannot run cars around vehicle and make tests. Around pedestrian and make tests, because first it's forbidden, and then it's very risky, so we have many problems for that. So we can have in simulation some validation with some metrics that we can imagine, but it's not reliable enough for us. So we try to see how we can test experimentally our algorithm. So I will present the work of Thomas Genzois. We will have his PhD next year on augmented reality. So if we do simulation-based testing, it's flexible, fast, cheap, safe, but not entirely realistic. If we do real-world testing, it's realistic, but complex, time-consuming, costly, and for our case, very dangerous. So we investigated the use of augmented reality to replace sensor outputs and test our software. So from perception to control, in our case, is for control. So the idea here is that we have to mix real-world perception, so that the car perceives the environment, maybe some obstacles, maybe a real pedestrian that is far. And we mix it with simulated data. And we have a sensor emulator that mixes simulated scene with real scene, so that the car thinks that it has perceived everything in reality. So we manage the fact that we have occlusions, and we manage the fact that we should not recognize if it's simulated or not. Okay. Here you see on the left a simulated pedestrian, but it is perceived as a real pedestrian using LiDAR sensors. So we can mix real pedestrians with simulated pedestrians, and we don't see, if you fuse both data, you don't see the difference between real pedestrian and simulated pedestrian. So it's quite realistic for us. We can obviously simulate other cars and mix other cars with pedestrians or real cars that we can perceive. And to link our work, what we will see at the end is that we can simulate crowds using the simulator we had, putting in this augmented reality and adding the control part that we decide to test on a real car, because in this case we can use the real car for the control algorithm on the real car. That imagine that it can perceive a crowd, but this crowd is simulated, so you have no risk, but it's more realistic than using only simulation. Okay, that's the end of my presentation.